When we look up, we see moons, planets, asteroids, pulsars, star clusters, nebulae, stars as big as whole solar systems, and millions of galaxies. You know what we don't see? Black holes. Because no one has ever seen a black hole. Black holes are deep, dark, swirling sinkholes of collapsed matter, a gravitational whirlwind that consumes everything and crushes it, a place where not even light can escape. Except, this isn't a black hole. This is an artist's idea of what a black hole might look like, or more precisely, the light around it called the event horizon. Think about TV shows and movies like Stargate SG-1, Lost in Space, Star Trek, even The Black Hole, and most famously Interstellar. They all have images of black holes, but no one's ever actually photographed one. So how close are we to taking a picture of a black hole? Taking a picture of a black hole is expensive, difficult, and takes a lot of smart people's time. You've probably never even thought about what a black hole really looks like because you thought this is what a black hole looks like, but it's not. So why are scientists so desperate to see one? Why does it matter? First, science. Second, black holes are incredible, and right now artists and filmmakers build conceptions based on what scientists tell them is important, but we don't know if these are right. These pictures are based on math, not in reality.
We've known about black holes since the early days of Einstein's theory, but until we actually see one, then there's a part of us that doesn't want to believe they're real.
This actually all started with that famous equation, E = mc squared. But math can only get us so far. I mean, we knew Pluto was out there since the early 1900s, and our best guess told us that it was a boring icy ball. Until we flew by it in 2016 and actually saw it. Imagine how we'll feel when we see a black hole with our jelly-filled light buckets. And this is what scientists are going to use to snap a photo of a black hole. The Event Horizon Telescope. It's not just one telescope, it's a network of many all over the planet. This effectively creates a single telescope as big as the Earth. The bigger the telescope, the more detail we can see, and the further away, which we definitely need to take the image of something like this black hole. Meet Sagittarius A star.
Sag A star is at the center of our galaxy. It's thousands of light years away.
There's a second object that we're also very interested in, and that is the black hole in the center of the galaxy M87, also known as Virgo A. M87 is an elliptical galaxy that's located about 17 megaparsecs away, so about 50 million light years away. That would be like trying to photograph an orange on the surface of the moon from the Earth, or trying to pick out individual molecules in a piece of paper in front of you.
And they do this with a whole array of radio telescopes, again, spread around the world. Not the kind you look through, though. They use radio wavelengths instead of visible wavelengths. It's a process called interferometry.
Interferometry is a general technique to take the signals from two separate receiving systems, in this case telescopes, and interfering the signals with each other.
The word interferometry is a combination of interfere and meter, or to measure. They're measuring a pattern of interference of the radio waves entering the telescope. By analyzing the interference pattern, the data from the telescopes can be merged together, and images can be filtered from all the noise. These astronomers are using very long baseline interferometry, meaning the radio telescopes are far apart, but are working together. Which brings us to April of 2017, when these astronomers pointed their telescopic array at the black holes in Sagittarius A star and M87 for 5 nights. So wait, doesn't that mean we took the picture? No, we didn't. We took the data. We're now starting to process the data into a picture.
Part of the difficulty of reconstructing an image is the fact that we don't have all of the data that we need.
The cosmic signals from the black hole that we're interested in are very weak. Most of what we're recording is the thermal noise from the receiver. So the data that we're interested in is roughly 1/millionth of all that data.
It is definitely a lot of astronomy, and it is a lot of computer science as well. So we're talking about hundreds of terabytes of data per station, and then add it all together, and that's petabytes.
A petabyte of data is 1,000 terabytes. That's a lot. That's 3,900 of the largest iPhones. It's so much that they can't even upload it. It's physical on hard drives. All that data has to be shipped to processing centers from the telescopes around the world, including at the South Pole, which has extreme weather, so scientists have to wait months to even receive that data. There are 2 sites working on the data, the Max Planck Institute for Radio Astronomy in Bonn, Germany, and here at the MIT Haystack Observatory outside Boston. Once the data is all in one place, the scientists have to correlate it. It's like watching a 3D movie, but where each eye is seeing something a little different. The scientists need to match them up with precise timing, more precise than atomic clocks on GPS satellites.
One of the possibilities is that this year's data won't be sufficient to provide a good image, but with the addition of next year, we will. Again, we won't know until we actually are at that point of the analysis.
With any luck, we'll see the first image of a black hole in 2018. If we can gather enough data, correlate it, and analyze it to find the image of something thousands or millions of light years away. And if we do that, what will we see?
The accretion flow will probably look more or less like a crescent, and that's because we're not viewing the accretion flow face on, and we're not quite viewing it edge on, but closer to edge on. So we really don't know what we will see. Was Einstein correct? We won't really know until we see the image.
If we produce a really nice picture, people will say, wow, so that's what a black hole looks like. That's cool.
So we are pretty close to seeing our first photographs of a black hole. If not in 2018, then maybe in 2019. What do you think astronomers will learn? What will it look like? Do you think it's going to be different than what we thought? Let us know, and thanks for watching Seeker.
Make sure to follow the page so you don't miss our next episode where we find out just how close we are to finding a cure for AIDS.
This virus is hiding in our DNA. And we've got a new DNA editing technique, CRISPR-Cas9. Why don't we just use that?
Are there questions out there you want to know how close we are to answering? Let us know down in the comments. And thanks for watching.